So let's take a look at parametric surfaces and their areas. Now, similar to having a vector function r of just one variable t, you can also have a vector function of two variables, or of two parameters u and v. And so the formula for that, or the standard formula, is going to be x in terms of u and v times I, plus a y equation in terms of u and v times j, and then plus a z equation in terms of u and v times k. So if we were to come up with parametric equations for this specific vector function, then we can say that x equals the x component, which is x in terms of u and v, y equals the y component, y in terms of u and v, and z equals the z component, z in terms of u and v. Now keep in mind, it doesn't always have to be in terms of u and v. You can set it to whatever parameters you want it to be. It could be x and y and z. It could also be x and theta. It just depends on the problem. And so now if you were to find a parametric representation, or in other words, a set of parametric equations for a plane that passes through a point, r sub naught, and then has two vectors a and b, then the formula to find a parametric representation is going to be r of u and v equals r sub naught, the point that the plane passes through, plus u times a, one vector, plus v times another vector b. So for these next set of problems, let's go ahead and find a parametric representation for the surface. So for number 1, we have the plane that passes through the point 1, 2, negative 3, and contains the vectors I plus j minus k and I minus j plus k. So notice we are given two vectors. We are given a point that the plane passes through. So the point is going to be r sub naught, and the two vectors, let's go ahead and call them a and b. Once again, the formula is r in terms of u and v, so the vector function in terms of both variables u and v is going to be equal to r sub naught plus u times one of the vectors a, and then plus v times another vector b. So plugging everything into the formula, we have r of u and v equals r sub naught. In component form, it's just going to be 1, 2, negative 3, plus u times the vector a. Now a is going to be I plus j minus k. So in component form, that would be 1, 1, negative 1. And then we have plus v times b. The vector b is I minus j plus k. So in vector form, or in component form, that would be 1, negative 1, 1. So now I can go ahead and rewrite 1, 2, negative 3. And then plus, I'm going to distribute the u and the v over. So then we'll get 1 times u is u, we get comma u, and then negative u, because negative 1 times u is negative u. And then plus, we'll get v, comma, negative v, comma, v. So then I can go ahead and add all these vectors together. So r of u and v, the vector function in terms of both of those variables, or both those parameters, is going to be equal to, now I'm going to add similar components, so we have 1 plus u plus v. So that is going to be the x component, comma the y component. We're going to add the y components of each vector. So 2 plus u and then minus v this time. So 2 plus u minus v, that's the y component. And then for the z component, we have negative 3 minus u plus v. So I'll write down negative 3 minus u plus v. So if we were to find parametric equations for this, the x is just going to equal the x component, so 1 plus u plus v. Y is going to equal the y component, 2 plus u minus v. And z is going to equal the z component, negative 3 minus u plus v. So now for number 2, we have the part of the hyperboloid x squared plus y squared minus z squared equals 1 that lies to the right of the xz plane. So notice we aren't given two vectors, nor are we given any point of intersection. But what we are given is the part of the hyperboloid. So we cannot use the formula that we used in the previous problem. Now, over here it says to the right of the xz plane. So if I were to go ahead and draw out the three-dimensional coordinate system, we have x, y, and z. The xz plane, if I just draw this in another color, is going to be something like this. So if we're talking about to the right of the xz plane, that is going to be where the y values are going to be positive, or where y is greater than 0. So this tells us the x and z values can be any real number, or any real value, but the y values have to be positive. Now since x and z can be any real value, I'm going to set my vector function and have the two parameters as x and z. So what we're really trying to do here is we're trying to make sure that all the parametric equations are going to be in terms of only x and z. Now the surface we're talking about is the surface of this specific hyperboloid. Since x and z are already in the equation, we can just say that x equals x and z equals z. Now since y is not one of our parameters, we need to put y in terms of x and z. So I'm going to go ahead and isolate y. So in this case, y squared is going to equal 1 minus x squared plus z squared. So then y equals plus or minus the square root of 1 minus x squared plus z squared. Now realize that y has to be greater than 0, so I can get rid of this negative and say that y just is going to equal the square root of 1 minus x squared plus z squared. So that is going to be the y equation, if I go ahead and rewrite that. So realize that all of these equations are in terms of just x and z, like what we set our parameters to. So those are going to be the equations, or the parametric equations for the surface. Now if I want to write it in component form, I can also write it as r of x and z equals the x component, which is x, the y component, which is the square root of 1 minus x squared plus z squared, and then comma the z component, which is just z. So now for number 3, we have the part of the cylinder y squared plus z squared equals 16 that lies between the planes x equals 0 and x equals 5. So the best way to find parametric representation for a cylinder is just to convert into cylindrical coordinates. So if I were to go ahead and graph out a cylinder in 3 dimensions, let's just pick the cylinder with the equation x squared plus y squared equals 1. So in this case, the base of the cylinder, or the circle, is centered at 0, 0, 0. If I go ahead and redraw that. And then we have the radius of 1. Now in this case, x is going to equal r cosine theta, y is going to equal r sine of theta, and z will just equal z when we convert into cylindrical coordinates, because whatever the z value is in rectangular coordinates is going to be the z value in cylindrical coordinates, because that's the axis of the cylinder is the z-axis. Now if I were to graph the surface that was given to us, y squared plus z squared equals 16, go ahead and draw another graph in 3 dimensions. This time, whatever variable is missing, that's going to be the axis of the cylinder. Since the x-axis is missing here, the axis of the cylinder will be the x-axis, and the radius squared is 16, so the radius is 4. So it's going to look something like this. The radius of the cylinder is going to be 4. So realize that on the left, the axis of the cylinder is the x-axis, and on the right, the axis of the cylinder is the z-axis. So in order to find proper parametric representation for this specific surface, we have to actually switch those two values, or switch the equations for x and z, because we've changed axes from the x to the z-axis. So we can say that x equals x, y is going to stay the same at r sine theta, and then z is going to equal r cosine theta. Now x is going to equal x, similar to how z equals z, because if we look at this graph here, whatever the x value is in rectangular coordinates, that's going to be the x value in cylindrical coordinates. Now we can only have 2 parameters, but in this case we have 3 variables, x, r, and theta. But the good thing is that we know what r is. R, or the radius, is going to be 4. So the final answer for the parametric representation of this specific surface is going to be x equals x, y equals 4 sine theta, and then z equals 4 cosine theta. Now we also need to add a couple more restrictions, because realize that we're looking for the part of the cylinder that lies in between the planes x equals 0 and x equals 5. So we have to say the x values range from 0 to 5, and our other parameter obviously is theta, that's the other variable. So theta, well, since it's a complete cylinder, obviously theta just ranges from 0 to 2 pi radians. Those are going to be the restrictions. Now the next set of problems are going to ask us to find an equation of the tangent plane to the given parametric surface. So given a vector function r in terms of 2 parameters, u and v, once again the equation is x in terms of u and v times I, plus y in terms of u and v times j, and then plus z in terms of u and v times k. Now in order to find an equation for the tangent plane, we need to find 2 tangent vectors, r sub u and r sub v. So the formula for r sub u is going to be the partial derivative of the x equation with respect to u times I, plus the partial derivative of the y equation with respect to u times j, plus the partial derivative of the z equation with respect to u times k. So we're basically going to take the partial derivative of each component with respect to u. And for v, it's the same process. We're going to take the partial derivative of x with respect to v times I, plus the partial derivative of y with respect to v times j, and then plus the partial derivative of the z equation with respect to v times k. And now the next step is to take the cross product of r sub u and r sub v. And so the result of the cross product will give us a normal vector which has the components a, b, and c. And let's say we are also given a specific point. Let's just call it x naught, comma y naught, comma z naught. So given a normal vector and a specific point, we can write the equation of a plane. And so once again, that's going to be a times x minus x naught plus b times y minus y naught, and then plus c times z minus z naught equals 0. And that's how we find the equation of the tangent plane. So for number 1, we have to find an equation of the tangent plane to the given parametric surface at the specified point. So the parametric equations are x equals u plus v, y equals 3u squared, and z equals u minus v, and the specified point is 2, 3, 0. So realize that we can also rewrite these parametric equations inside a vector function, r, in terms of two parameters or two variables u and v. So once again, that's going to be equal to the x component, which is u plus v, times I, plus the y component, 3u squared, times j, and then plus the z component, u minus v, times k. So there are two things we need to find here. We need to find r sub u, and we need to find r sub v. So let's go ahead and first find r sub u. Remember, for r sub u, we're going to take the partial derivative of each component with respect to u. So for r sub u, we take first the partial derivative of the x component with respect to u. That's just going to be 1 times I, plus the partial derivative of the y component with respect to u. So that's going to be 6u times j, and then plus the partial derivative of the z component with respect to u. That's just going to be 1 times k. So rewriting it, we get I plus 6uj plus k. Now for r sub v, we need to take the partial derivative of the x component with respect to v. So that's going to be 1 times I, plus the partial derivative of the y component with respect to v. That's going to be 0 because there's no v variable. Then plus the partial derivative of the z component with respect to v. That's going to be negative 1 times k, or negative k. So rewriting it, we have I minus k. Now the next step is to take the cross product of r sub u and r sub v. So once again, when we take the cross product, we need to set up a matrix. We have I, j, and k on the top row. Since r sub u is being multiplied first, we'll put its components down first. So from left to right, we have 1, 6u, and 1. And then for r sub v's components, we just have 1. The y component is 0 because there's no j unit vector, and the k component, or the z component with the k unit vector, is negative 1. So now we can put it in determinant notation. So when we find the determinant, we take the top leftmost value, so we have I times a smaller matrix, cross off its row and column. What we have left is 6u, 1, and 0, negative 1. Second term's a negative, so j times, we cross off its row and column. The smaller matrix is of 1, 1, and 1, negative 1. Third term is a positive, so plus k times, let's cross off its row and column. What we have left is 1, 6u, and 1, 0. So now we can go ahead and cross multiply. So we get I times 6u times negative 1 is negative 6u, minus 0 times 1 is 0, minus j times 1 times negative 1 is negative 1, minus 1 times 1 is 1, and then plus k times 1 times 0 is 0, minus 1 times 6u is 6u. So then we get negative 6u minus 0 is negative 6u, so then we get negative 6u times I. Negative 1 minus 1 is negative 2, so if I rewrite it as negative 2, the negatives will cancel, so we get plus 2j, and then we have a negative can come out front, so minus 6u times k. Now the next step is to simplify this normal vector. Notice we still have the u variable, and we need to get rid of that so we can simplify the vector. So what we can do here is, given the point 2, 3, 0, realize that it has its x-coordinate, the y-coordinate, and the z-coordinate. We can plug it into the parametric equations that were originally given to us to find what the u value is. So notice y equation, or the y equation, only has one variable in it, so we can go ahead and use that equation first. Since the y-coordinate is 3, we can say that 3 equals 3u squared. So then u squared equals 3 over 3, or 1, and then u equals plus or minus the square root of 1, which is plus or minus 1. So now we have to go ahead and plug it into another equation, because even though it says u's can be plus or minus 1, after plugging into all three equations, it can only be one of them. It can either be positive 1 or negative 1. So let's go ahead and try the x equation next. So the x coordinate is 2. So we have 2 equals u plus v. Now we can try either one of them. Let's go ahead and try the positive one first. So then 1 plus v. So then v equals 2 minus 1 or 1. So u equals plus or minus 1. That means v can equal 1. Now let's try when u is negative 1. So in this case we have 2 equals negative 1 plus v. So then v equals 2 plus 1, which is 3. So v can either equal 1 or 3. So now we can go ahead and plug it into the last equation, the z equation, to figure out which u and v value it is. So z is going to equal u minus v. In this case the z coordinate is 0. So 0 equals u minus v. Now what value could we plug in for u and v to get us a value of 0? Well, both u and v in this case have to equal positive 1. So obviously 0 equals 1 minus 1. So in this case u equals 1, v equals 1. So now we can plug in, since we don't have the v variable in the vector or in the normal vector, we don't even have to worry about that. We just have to plug in 1 for u into the normal vector. So we have negative 6i plus 2j and then minus 6k. So if we write it in component form, we can also write it as negative 6 comma 2 comma negative 6. So that is going to be the a, b, and c values. And so if I go ahead and rewrite the specified point, we have 2, 3, 0. And so now given a normal vector and a specified point, we can write the equation of a tangent point. So the equation is going to be a, which is negative 6. So negative 6 times x minus the x value of the point, so 2, plus b value, which is 2, times y minus the y value of the point, or the y coordinate of the point, which is 3. And then plus c, which is negative 6, times z minus the z coordinate, which is 0. And that will equal 0. So now we can go ahead and solve. So if I distribute over the negative 6, we'll get negative 6x plus 12, and then plus 2y minus 6, and then we have, I can get rid of the plus because we have a negative here, so then minus 6z, and then plus 0. That's going to equal 0. I can get rid of that 0. 12 minus 6 is 6. If I go ahead and subtract that to the other side, we'll get negative 6x plus 2y minus 6z equals negative 6. Now I'm actually going to go ahead and make the right side of the equation positive. So we get 6x, if I divide everything by negative 1, 6x minus 2y plus 6z equals 6. And then I'm going to go ahead and divide everything by 2. So we get 3x minus y plus 3z equals 3. And that's going to be the final answer. Now the next problem will be about finding the surface area given parametric equations. And so the formula is just going to be the double integral described by a region D of the magnitude of the cross product of r sub u and r sub v, dA. So for number 1, let's go ahead and find the area of the surface. So we have the surface with parametric equations x equals uv, y equals u plus v, z equals u minus v, and we're given that u squared plus v squared is less than or equal to 1. So once again, the formula for the surface area of parametric equation in terms of u and v is going to be equal to the double integral described by the region D of the magnitude of the cross product of r sub u and r sub v times dA. So we need to go ahead and find the cross product and find the magnitude of that cross product. So let's go ahead and first find r sub u. Now remember, for r sub u, we're just going to take the partial derivative of each equation with respect to u. So partial derivative of the x equation with respect to u is going to be v, so v times I, plus partial derivative of y with respect to u, that's just going to be 1 times j, and plus the partial derivative of the z equation with respect to u, that's just going to be 1 times k. So if we go ahead and simplify, we get v times I plus j plus k. So now let's find r sub v. So r sub v is going to be the partial derivative of the x equation in terms of v, so that's going to be u times I, plus the partial derivative of the y equation with respect to v, that's going to be 1 times j, plus the partial derivative of the z equation with respect to v, that's going to be negative 1 times k, or negative k. So if we simplify, we get u times I plus j, and then minus k. So now let's go ahead and find the cross product of r sub u and r sub v. So once again, we're going to go ahead and set up a matrix here. So r sub u, we have I, j, and k on the top, and then r sub u, its components are going to be v, 1, and 1. and then r sub v's components are going to be u1 and -1. So let's go ahead and find the determinant. So we have the top leftmost term, I, times the smaller matrix. We cross off its row and column. What we have left is 1, 1, 1, -1. Second term is a negative. We have j times the smaller matrix. When we cross off its row and column, what we have left is v1 and u -1. Third term is a positive. We cross off its row and column, and what we have left is v1 and u1. So now we can go ahead and cross multiply and evaluate. So we have I times 1 times -1 is -1, minus 1 times 1 is 1, minus j times v times -1 is -v, minus u times 1 is u, plus k times v times 1 is v, minus u times 1 is u. So when we simplify, -1 minus 1 is -2, so we have -2i, -v minus u. Now I can factor out a -1, so we have -1 times v plus u. Realize that negatives will cancel, so we basically have plus, or if I rewrite it as v plus u times j, and then plus we have v minus u times k. So if I go ahead and rewrite it in component form, we have -2 comma v plus u comma v minus u. So now we need to go ahead and find the magnitude of the cross product. We already found the cross product, now we take the magnitude of this. So in order to find the magnitude, once again we're going to take the square root of the x component squared, so -2 squared is going to be 4, plus the y component squared. So if we go ahead and FOIL that, we get v squared plus 2vu, and then plus a u squared, and then plus the z component squared. So if we go ahead and square v minus u, we can FOIL it, and we'll get v squared minus 2vu, and then plus u squared. So now we can go ahead and simplify. So 2vu minus 2vu will cancel, and so we're left with the square root of 4 plus, now v squared plus v squared is 2v squared, and then u squared plus u squared is 2u squared. So square root of 4 plus 2v squared plus 2u squared is what we're left with. So rewriting the double integral, we have the surface area is going to equal the double integral described by the region D of the magnitude of the cross product, which we have found to be the square root of 4 plus 2v squared plus 2u squared. So now what we have left to do is to find our bounds of integration. So I'll go ahead and erase D here. So we're given that u squared plus v squared is less than or equal to 1. So instead of x and y, we have u and v. So we can treat it the exact same way where instead of the xy axis, we have the uv axis, where u is going to be the x-axis, v is going to be like the y-axis. Now if we think about u squared plus v squared is less than or equal to 1, think about x squared plus y squared is less than or equal to 1. So that just describes the region with a circle, or the region of a circle that's centered at 0, 0, has a radius of 1. And we're looking at all the region inside of it. Now since we're dealing with a circle, it's easier to evaluate the double integral in polar coordinates. So instead of u and v, this time we have r and theta. So for the radius, realize that the bounds for r are just going to be from 0 to 1, and the bounds for theta, since it's a complete circle, is just going to go from 0 to 2 pi. And we also need to convert what's inside the integral into polar coordinates as well. Now if I go ahead and convert this, we have 2, I go ahead and factor out a 2, so 2 times v squared plus u squared. So think about v squared plus u squared as y squared plus x squared, or x squared plus y squared. Now x squared plus y squared obviously equals r squared, so we have 2 times r squared. So basically what we have left is the double integral. Now when we convert polar coordinates in double integrals, we have to multiply by that extra r variable. So we have r times the square root of 4 plus, and then we simplify this entire thing down to 2r squared. So 4 plus 2r squared. And then once again, since both of the bounds don't have any variables in them, we can go ahead and choose which one to put first. Let's just go ahead and put the r bounds first. So from 0 to 1, we'll put dr, and then d theta, which go from 0 to 2 pi. So let's go ahead and evaluate this. So we have the integral from 0 to 1 of r times the square root of 4 plus 2r squared dr. Realize this is just a u substitution problem, so if u is equal to 4 plus 2r squared, then du is going to equal 4r dr. So then isolating dr equals du over 4r. If I go ahead and plug that back into the integral, we get the integral from 0 to 1 of r times the square root of u, since we set u to be equal to 4 plus 2r squared. And I'll rewrite that as u to the 1/2 times dr, which is equal to du over 4r. Realize the r's will cancel. 1/4 can come outside the integral as a constant. So we get 1/4 times the integral from 0 to 1 of u to the 1/2 du. Now the integral of u to the 1/2, we do have 1/4 as a constant. Integral of u to the 1/2 is 2/3 u to the 3/2. 2 over 4 is 1 over 2. 1 over 2 times 1 over 3 is 1 over 6. So we're left with 1 over 6 times u. We can plug that back in. So 4 plus 2r squared to the 3/2 power. Let's go ahead and evaluate that from the r bounds of 0 to 1. So we get 1/6 times, when I plug in 1 for r, we'll get 1 squared is 1, 1 times 2 is 2, 2 plus 4 is 6. So 6 to the 3/2 power, minus, when I plug in 0 for r, we'll just get 4 plus 0 is 4, and 4 to the 3/2 is going to be the square root of 64, which is 8. So now we can evaluate the outer integral from 0 to 2 pi, this time with respect to theta. Now this entire thing is a constant, so the integral is just going to be 1 over 6 times 6 to the 3/2 minus 8 times theta. So let's go ahead and evaluate that from the theta bounds of 0 to 2 pi. So when I plug in 2 pi, I'll just rewrite the entire thing. 1/6 times 6 to the 3/2 minus 8 times, so now when I plug in 2 pi for theta, we get 2 pi, minus when I plug in 0 for theta, we get 0. So then when we simplify, we just get 2 pi times 1 over 6, so 2 over 6 is 1 over 3. So we get pi over 3 times 6 to the 3/2 minus 8. Now I can simplify this even further. If I rewrite 6 to the 3/2, I can rewrite it as a square root of 6 cubed, which is 216. So the square root of 216. Now 216 can be divided into square root of 36 and square root of 6. Square root of 36 is obviously 6. So the final answer is going to be pi over 3 times 6 times the square root of 6 minus 8.